Hello everybody. So in this video we will be looking at normal distributions. Normal distributions are also called Gaussian distributions, and they are a family of symmetrical bell-shaped density curves defined and they have two parameters, mu and sigma. And mu is really the mean of the distribution, and sigma is the standard deviation of the distribution. The PDF function, the density function for Gaussian distributions, they have the following form. It's 1 over sigma root of 2 pi times e to the negative half x minus mu over sigma squared. Here E represents the number 2.71828 dot dot dot. So this is an exponential function that gives us the PDF, or the density function for Gaussian distributions. So if I have a variable x, and if the PDF function for x is given by this function, then we say that x is a normal variable, and x has normal distribution with mean, mu, and standard deviation equal to sigma. So mu and sigma, they are called the parameters of this of the Gaussian distribution. So if you change mu and sigma, you change the distribution. So here are two figures where we have drawn two different PDFs with different mu's and sigmas. So in the first case, the sigma is bigger than in the first figure, sigma is bigger than the sigma in the second figure. And the density curves here, you can see they are bell-shaped, and it's symmetric. So symmetric about the mean. So the part of the curve on the right side of mu is the reflection of the left side of mu. So in other words, the right side of the density curve is a mirror image of the left side of the density curve, and the mean is exactly where the midpoint of the curve is. The area under the entire curve is equal to the total probability, which is 1. And the area on the right side of mu is the same as the area on the left side of mu. A lot of variables in the real world are normal, and for example, a probability distribution of height of a population is normal. We will see later why many variables are normally distributed. So in the first figure, we have fixed the mean, and then we have drawn the Gaussian distribution for sigma equal to 2, 4, and 6. And you can see the bigger the sigma is, the wider the curve is, and then you can see that if you increase sigma, you are decreasing the height, and you're making the curve wider. On the other hand, if we fix sigma, we are fixing sigma, and then we pick different values of mu. What it does is that the spread is the same in all three cases. It's just that the green and the red one are just horizontal shifts of the blue one. Here is the 68, 95, 99.7% rule. So what it says is that 68% of the area below the density, below the normal density curve is within one standard deviation from the mean. So that what that means is that 68% of all observations are within one standard deviation sigma of the mean mu. So that is, if I have that height is normally distributed with mean height equal to 64.5, then, and let's say that the sigma in this case is 2.5, then 68% of the observations of height will be within one standard deviation from the mean. So that means 68% of the observations will be between 64.5 plus 2.5 and 64.5 minus 2.5. So 68% of the observations will be between 62 and 67. And 95% rule means that 95% of the area below the density curve here will be within two standard deviations from the mean. So in other words, here again, if you think of x being height, and we assume that the x is normally distributed with the mean 64.5 and the standard deviation 2.5, then 95% of the observations of height will be within two standard deviations from the mean. In other words, so this is two standard deviations away from the mean on the left, and this is two standard deviations away from the mean on the right, and 95% of the observations or the area fall in between these two numbers. And then 99.7% of the 99.7% rule is similar. It's just that now we are talking about 99.7% of the area or 99.7% of the observations. One thing that I want to mention here is that when we have a variable x that has normal distribution, when we have a variable x that has a normal distribution, we're going to denote that by writing n mu sigma. So if I say x has distribution given by n mu sigma, it means that x has normal distribution with mean mu and standard deviation equal to sigma. The standard normal distribution is the normal distribution where the mean is 0 and the standard deviation is 1. And usually when the standard normal variable is denoted by z, or it's called the z-score. So n01 is called the standard normal distribution. If x has normal distribution with mean equal to mu and standard deviation equal to sigma, then its z-score, the z-score of x, is defined by z equal to x minus mu over sigma. So it turns out that if x has normal distribution with mean and standard deviation given by mu and sigma, and if we define z in terms of x in this way, then z will always have normal distribution. So for example, let's say that x represents height and x is normally distributed with mean 64.5 and standard deviation equal to 2.5. If we take z to be x minus 64.5 over 2.5, then we are going to get the standard normal distribution. So this is for any normal distribution. And the reason we like standard normal distribution is that, when we want to calculate probabilities, we need to be able to find the area below the density curve. And for the standard norm, so we can't possibly, so there are tables that contain estimated values of areas below the density curve, and you don't want to do it for any given parameters. So you want to really do it for only one normal distribution, and that's the standard normal distribution. So this table here gives us the areas below the standard normal curve. And so the way you want to read this table is the following. So this number here, 0.0082, that is the area below the standard normal curve to the left of the number negative 2.40. So the area to the left of negative 2.40 in the okay. So the area below the standard normal curve to the left of negative 2.40 is equal to 0.0082. Similarly, 0.0080, that's the area to the left of negative 2.41. And 0.0069, that's the area to the left of negative 2.46. So again, this table is for the standard normal distribution only. And you will find this table in the back of your text as well. Symmetry. So like we said, this is a bell-shaped and it's symmetric about the mean. So if you look at the area to the left of a z is the same as the area to the right of negative z, or I can say the area to the right of z is the same as the area to the left of negative z. So if I look at the area to the left of negative 2.33, that area is the same as the area to the right of 2.33. Also, if we want to find the area to the right of z, then we can find that because the table that we just saw, it only gives us areas on the left side of z values. And if we want to find the area to the right of a z value, then that's the same as 1 minus the area to the left of the same z value. The area between two values of z, z1 and z2, would be the area to the left of z1 minus the area to the left of z2. So for example here, if I want to look at the shaded area between 1.4 and 2.2, we can find that by first finding the area to the left of 2.2 and the area to the left of 1.4, and then subtract the smaller one from the bigger area to get the shaded area. And that's the probability. The area between z1 and z2, that's basically the probability probability that z is between z1 and z2. All right, so let's do an example now. So let's say we want to find what's the probability if we pick one woman at random that her height will be between 68 and 70 inches. So let's say the population we are looking at is the population of women and let's say in the United States, and let's say the height is normally distributed. It has normal distribution with mean 64.5 and standard deviation 2.5. So again, we are assuming that the mean is 64.5 and sigma is 2.5. And we want to find the probability that x is between 68 and 70. So to do that, the first thing I'm going to do is, because I want to use the table for the standard normal variable, and so I'm going to find the z-score for these two values of x. So z, remember, is x minus mu over sigma, and for x equals to 68, z would be 68 minus 64.5, that's the mean, divided by the standard deviation, and that's 1.4. For x equals to 70, z would be 70 minus 64.5 over 2.5, which is 2.2. So these are the z-scores associated with 68 and 70. And so the probability that x is between 68 and 70 it would be the same as the probability that x is between would be the same. So the probability that x is between 68 and 70 will be the same as the probability that the z-score is between 1.4 and 2.2. So how do we find that? Well, so like I said, the probability that x is between 68 and 70 is the same as the probability that the z-score is between 1.4 and 2.2. And now this probability is for the standard normal distribution, so we can find it from the table that we have for the standard normal distribution. So now it turns out that the area to the left of 2.2 is 0.9861, and the area to the left of 1.4 is 0.9192, and so the area in between 1.4 and 2.2 would be 0.9861 minus 0.9192, which is 0.0669 or 6.69%. And let me show you that in the table. So notice that the probability that x is less than 2.2. So you go to 2.2 here, so 2.20 right here. So this is the area to the left of 2.2, and the area to the left of 1.4 is 0.9192. So this is 1.40. This is for 1.41. This is 1.42, and so on. So this is the one that we need. So we get 0.9861 and 0.9192, and from that we get our answer. Okay, we don't have to use the standard normal distribution table. We could also use the calculator to do it. So here are the instructions for using the TI-84 to calculate the probabilities for a normal distribution. All right, so now we look at the inverse problem. That is, here's the question we want to answer. Let's say, so here, let's say the area is given, and I want to find the corresponding z-score. That is, what is the z-score with area 0.02 to its left, let's say. So the 0.02 is the area given, and I want to find the z-score so that the area to its left is 0.02. Well, what I do is, in the table I find the number 0.02, so within the table. So all right, so here is 0.02. So if you look at the last row and the column for 0.05, right? So you see that 0.02, right about, so this value is right about 0.02. So I'm going to use that as an approximation of this area. So this is the area to the left of what z-score? Well, it is the area to the left of the z-score negative 2.05. So negative 2.05. So this is the area to the left of negative 2.05. So I have a typo here. It should be negative 2.05. All right, so let's do another example like that. So I want to find the z-score with area 0.0125 to its left. So again, I go to the table. I want to find the area equal to 0.0125. So let's find 0.0125. So right here you can see that I have 0.0125, and that's the area to the left of minus 2.2. So minus 2.24, minus 2.24. Okay, so you can see how you can find the z-score given the area. So this is known as the inverse problem. Let's do an example. Let's say we have a chocolate bar, and the weight on the wrapping indicates that its weight is 8 ounces. And so the whole hazelnuts, they vary in weight. So how can they guarantee you 8 ounces, right? And so let's see how they would guarantee 8 ounces on their package. So to avoid customer complaints and lawsuits, the manufacturer makes sure that 98% of all chocolate bars weigh 8 ounces or more. So 98% of all chocolate bars must weigh 8 ounces or more. The manufacturing process is such that the distribution of weight is normal, and the standard deviation is 0.2 ounce. So the question then is, so the standard deviation is known, and the question is, how should they calibrate their machines to produce bars with a mean mu such that the probability that X is less than 8 ounces is 2%, right? So remember, they want to make sure that 98% of the chocolate bars weigh more than 8 ounces, right? So knowing that your manufacturing process has this variability in weight given by sigma equal to 0.2 ounce, the question is, what mean weight of the bars will ensure that no more than 2% of the bars will weigh less than 8 ounces. So again, what value of the mean weight will ensure that no more than 2% of the bars will weigh less than 8 ounces. So how do we answer this question? So basically we know sigma, and we know what level of accuracy we want, which is 2%, and then we need to calibrate our machines to achieve certain mean weight. So again, what mean weight should we require to ensure that no more than 2% of the bars will weigh less than 8 ounces? All right, so here's the problem, right? So we have this, the weight is normally distributed where the standard deviation is 0.2 ounce, and we only want 2% of the bars to weigh less than 8 ounces. So that means the area to the left of 8 ounce should be 2%. All right, so to answer this question, again, we are trying to find what mean weight mu do we require so that no more than 2% of the bars will weigh less than 8 ounce. So that's that. So what we know the area under the density curve, 2%, which is 0.02, and we know X, which is 8 ounce, and we need to find mu. So what we do is we go to our standard normal distribution table and we find the z-score associated with the area 0.02. And so let me go to the z-score again. So notice that if we look at the the z-score with area 0.02 to its left is negative 2.05, right? Negative 2.05. So the area to the left of negative 2.05 under the standard normal distribution curve is 0.02. So we know that the z-score with a left area of 0.02 is roughly given by negative 2.05. Now we know that x is equal to x minus mu over sigma. So from this formula, I can solve for x and I can solve for mu, and find that mu would be x minus z times sigma. Now x is 8. We found z-score to be negative 2.05 and sigma is 0.2. So we find that mu is 8.41 ounce. So that means that if we require the mean weight of the bars to be 8.41 ounce, then we will ensure that no more than 2% of the bars will weigh less than 8 ounce. So then 98% of the bars will weigh more than 8 ounce. Okay, so this is it. This is all I have to say on normal distribution, and I'll in the next video we will start to look at the variance and standard deviations for distributions. So we'll look at mean of a random variable, law of large numbers, variance of a random variable, and rules for means and variances. So that will be in the next video. So I'll see you then. And if you have any questions, please feel free to bring them to the next class. All right.